Our talk today is called Serverless Ops, Bye-Bye Bash, Hello Go. Obviously, the focus here is going to be on moving your operations away from legacy bash scripts and into something more stable and repeatable, written in Go. I plan to go at a relatively decent pace, so I would prefer if you interrupt me along the way with questions, okay? I'm going to make some assumptions about what we already know, and inevitably I'll be wrong. But my first assumption is that probably all of you know Go better than me, and you'll see why when we get into Lambdas. So, what's in it for you and what you can hope to learn today? I'm going to give you an example that is a generic pattern that you should be able to use across any cloud provider, as long as that cloud provider provides access to events and workflow management and functions, which the major ones do. Of course, this is the Amazon building. I work for AWS, so the examples are going to be in AWS. The code is going to be specific to AWS. But I'm aiming for a generalizable principle here that you can see. I'm also going to give you an example specific to AWS of how to test your operations, because it's a little bit different from what you might run into as an application developer if you haven't worked in cloud operations before, specifically Lambda. Again, that pattern, I'm going to show you that pattern in a generic sense and in a specific sense that you can take away, and that complete workflow with code in Go. And then as part of the Q&A, I will also dive into the code there to show you some more fine-grained examples of what's happening behind the scenes. So then a quick, more of an agenda of order will go. We'll talk about what's happened to the shell. The question we get, you can't call it serverless because there's still servers. Yes, there are, that's not the point. Why you should use serverless to manage your operations, and why you should use Go to manage your operations. Again, how to test, the general pattern, and a specific example that captures a DynamoDB backup event from AWS backup and automatically restores that backed up table using a replacement pattern. So you can use this for DRBC testing, you can use this for populating sub-production environments, etc. Real quick about me, probably the only things you care about are that I'm a developer advocate for serverless at AWS, which means if you have questions about our services, this is Lambda, step functions, event bridge, SQS, SNS, orchestration, what serverless means, I'm here for you. If you have things that you would like to see that we don't currently do, I am your route back to the product team directly. So please give me that feedback so that we can continue to improve that entire suite of products and help you build more effectively. And then this is my Twitter handle. So if you like serverless content, I post things at various levels there, from my partners and my teams to just ridiculous nonsense technical thinking about Lambda and serverless and how we can do it. So where's my shell? Back in the day, we all had Bash. Anybody use 3270, like the IBM terminal into? Yeah. So EBC, DIC, and all this stuff, right? So literally, the terminal used to be a physical terminal. That's what I started on. And then we moved on to running Shell and X Windows on HPUX and Solaris and all of these things, right? And we got really comfortable because we had hands-on and we felt comfort around that. There was a state. We did something, we saw the state change. And it was a one-to-one instant interaction. But then we picked everything up and moved it to the cloud. And part of being in the cloud is securing everything. And so for the most part, your instances will be inside private subnets, which means there's no way for you to directly SSH into. So then we put these bastion instances in, or jump boxes if you were using Windows for RDP. And then you still were able to get that level of hands-on server hugging happiness, right? And then we got to containers. And if you're running containers on an orchestration platform that you've rolled yourself, then you can have access to those hosts that run it. You can SSH into there, and then you can run a Docker exec and get into the container. But if you move to something like Amazon Fargate, where it's completely managed, there is no option for you to get in there. And the in-between options like Kubernetes allow you to do sidecars and things that still give you the access, but they violate the principle of one container, one function. So you can see how the shell just keeps getting further and further away from us, but it's sort of there in the last reach. How do you SSH into DynamoDB, right? How do you SSH into S3? You can't. Like, the concept is just gone. You can no longer put your fingers on the server and change the state and see it happen. So with this bash, the born-again shell, and other things that were very specific to that shell concept begin to lose their relevancy. And when you look at scripts that are written in bash or shell or C shell, you can tell that they are being wedged into cloud operations. It's not a natural fit. So, yes, there are still servers and serverless. Happily, we take care of managing, patching, all of this stuff for you. But when we talk about serverless, we talk about 4 principles. The first is that there's no infrastructure provisioning and no infrastructure management. So if you have to define a VPC, if you have to think about IP address, subnet ranges, if you have to think about instance sizes, types, all of these types of things, that's not serverless. If you have to commit to, I'm going to run this thing all the time, that's not serverless. Automatic scaling. If you have to pre-think about, okay, I have 100,000 transactions per second, I know that my server can sustain 25,000 per second, so I need to provision at least 4, but then I need extra redundancy for spikes, right? You no longer have to think about this. Serverless elastically scales in and out without you doing that configuration or that pre-provisioning up front. Pay for value. This means there's a direct correlation between what you consume and what you pay. So if you consume nothing, you pay nothing. And as you consume more, you pay more. This does a couple of things for you. First off, it lets you prototype very quickly and eliminate the costs associated with it. It also lets you focus using cost on where you should optimize, right? So when it comes time to optimize your code, you can legitimately look at what is my most expensive function to run. Or you can look at it and say, okay, this is a slow function, but it only costs me $35 a year, and it would take me 8 hours to refactor it. It's not worth it, right? I'm just going to let it run slow because it doesn't impact latency to my users, or it's like a processing backend job. And then finally, highly available and secure. And the claim that I will make and support, especially the more of these technical details that I read, is that if you care about building a secure application, you should be building a serverless application. You can prove mathematically that it is more secure because you can cut down your attack surface. You cut down the number of things that your application has access to. You cut down the amount of complexity that you have to reason about in your mind at any given time. And then you can begin to do things like property-based testing. And so provable security for your critical applications becomes possible. And then the other parts that just do things like load an image that's not sensitive from a bucket somewhere, you don't need to go over there and prove security. But you also don't have access to your financial data from the application that pulls that data out of that bucket. So the blast radius is much, much smaller. So why do it for ops? I'm giving you all these reasons that it's great for applications. Why is it good for ops? And this is the responsibility model that we talk about. And normally in an application, we end up over here on the right, which is all you have to worry about is your application code and your business logic. The same thing holds true for operations. Because if you're running classic operations, you need to spin up an EC2 instance or your provider's instance or a container or something that every night at 1 a.m. runs your cron jobs, and you need to think about these things. But what happens when the process in that container dies and doesn't restart? Or when the instance goes down and the metadata they used to start up is no longer there. So we have CloudWatch events, which essentially can replace cron that fire timed events as you define, or events in response to other activities. And you can use that as the basis from which to begin your operations. And then the rest of these patterns, the workflows, the step functions, and the individual operations that you do flow out of there in a serverless manner. So operations and automation tasks are irregularly executed. This means leaving that instance running all the time, even if you're only executing tasks every 15 minutes, is incredibly wasteful. It's environmentally wasteful, it's cost wasteful, and it introduces opportunities for attack, right? Because typically your ops instances are highly permissioned. They have the ability to terminate, to replicate, to restore all of your data. So leaving that up represents a much bigger vulnerability. When you run something serverlessly, it's native to the platform that you're operating in, whether that's ours or another provider's. So you're getting the benefits of IAM built in. You're getting the ability to execute function calls from SDKs that are tightly integrated. And again, that takes me to service integration. So this is when one managed service calls another managed service. So you can post a request to API Gateway, and it can write the body of that request directly into DynamoDB without you putting a Lambda function in the middle. This means 0 lines of code written, which means 0 lines of code to debug, right? And then again, the fine-grained access permissions that I talked about earlier. If you have a function that needs to back up a DynamoDB table, you can give it the permission only to create a backup only of this resource, rather than having permission to back up all of your tables, back up all of your RDBMS, etc. And then logging. When you use your cloud provider's integrated services like this, you get integrated access to the logging. So however you aggregate that later, whether you put it into Splunk or whether you use the cloud native features that are there for you, you get all of that built in out of the box. So for example, with Lambda and Go, anything that you write out to, well, with any Lambda, anything that you write out to standard out goes directly into your logs. Just goes in as a CloudWatch entry. So you can go back and debug with that later. So with all that said, why use Go for operations, especially in the cloud? A very important case here is the long support life. So the designers of Go made the contract that Go 1.x will always work with Go 1.x. It's a true semantic version. So if you wrote a Lambda the day that we announced Go 1.x support, that Lambda would still run today. And I think at that time it was version 1.7 that was out, and now we're about to see 1.14. So in the meantime, we've seen other versions of other runtimes come into existence and be deprecated, like certain versions of Node.js and then Python in the block. Right? So Go has this long support life, which is really important when you're writing something that you expect to stay around and manage your infrastructure for you. Concurrency, of course, in the cloud, there's rarely, if ever, one of anything. We're typically dealing with collections and sets of things, whether those are your instances or security group rules, etc. Right? So whenever you need to deal with them, it's you set up the model, you kick off a Go routine for each one, and you take advantage of that concurrency. Type safety, as we'll see later, when you use these workflow management tools together, the best thing you can do with a function is just expect that your data is good, fail if it isn't, expect that your operation succeeds, return the error if it doesn't. The pattern is basically just following the happy path all the way down, checking for that error, and then returning it rather than handling it. This really simplifies your code, right? Restore the backup. If that fails, return that error. And then your orchestrator handles that error. Why did it fail? Is it a service not availability error? Do we retry with a backoff? Was it a permissions error? Send a notification so that you can check IAM, right? But it lets you, at the function level, think about only what is the exact thing that I'm trying to do right now. And then finally, developer joy, right? Like we're all here after work on our own time because we like writing in Go. So it's a great language to use with the cloud, and it's dedicated. So testing our ops. Everybody has used dependency injection in Go, right? So you have receiver functions and types. When you do any sort of hello world example with cloud infrastructure, it doesn't give you, it doesn't give you this dependencies. It just gives you the handler, and it has lambda.start handler. I apologize if this is a bit small. The slides will come around. And I'll show you the code later that we can blow up and we can look at a little more. One thing that we've done in our SDK is for every service that we have, in this example, step functions, SFN, we've provided you with an interface for that as well. So the best practice is to use that interface to write your functions. So when you get a Lambda here, the execution environment downloads your code, begins to run whatever's in your main, and then once it gets to this point, it's available to handle requests. So you do your initialization, in this case up here, to handle your request, and you can pass that in from your test instead. So if you look over here on the right, you create a dependency with a mock start, and in this case, we're just returning this predefined output that we have. And when you call start execution over here, it will use the dependency in a test, but it will instantiate a true client when you do it in production. This will become more clear with an example, I hope. I'll go ahead and show you an example of how it's normally generated without this, and then we'll change it. So the general pattern for orchestration of workflows in the cloud uses classic state machines, right? It can be in a number of finite defined states, and it can transition between them. In AWS, this is called step functions. Other cloud providers have their own versions. But you have some sort of event, because again, all of this is event-driven infrastructure. So you have some sort of event that initiates this requirement. You have a nightly backup. You have a security alert that tells you that you need to remove an instance from your group and put it into your forensic subnet. You have some sort of event that starts this workflow. And then you do the thing. And those things that we're doing for operations, by their nature, take a lot of time. Right? You're taking a snapshot of a database that's several gigabytes or several terabytes. Even in the fastest, I think it takes 41 minutes to restore an Aurora snapshot, right, with an empty database. So you've got this defined back-off and retry period that you need to wait for. In the meantime, you're checking for completion and just waiting until you can move on from there. With step functions and the other orchestration tools, they handle this back-off for you. So you don't want to be writing exponential back-off inside your code, which is great because that's something that you just write over and over and over, and it introduces a lot of opportunities for error. Instead, you let step functions handle those back-offs. And all the Lambda function knows is, I'm checking the status of this restore. You give me a table name, I go out, I check the status, and then I return whatever the status is, and that's it. I don't know how many times I've been called. So again, some specifics to step functions. If you use it, think about it like the main function of a normal procedural or imperative application. It's the part that handles looping, it's the part that handles distribution of tasks, it's the part that handles retries and errors. So whenever you get errors back, there's a lot of paths you can go down with it. So this is an example that's available online now in GitHub. I'll give you the link for it later. And it all starts with this event. This is an event that is provided to us from a service called AWS Backup. And what we've done with this is we've subscribed to the backup completed notification. So we don't care about when a backup starts. We don't care when a backup fails. We don't care about restores. We don't care about backup deletions. All we get are that event that, hey, your backup's been completed. This is the full message, which contains some data we'll use. This is the ARN, which is the resource locator, and this is the thing that was originally backed up. And then these are parameters that we pass to the step function. The source pattern is just a regular expression, so that matches ones that we care about. So typically like dash production, if you're naming your tables. The replacement pattern is what you want to replace it with. In the example, we use dash staging. So if you have customers dash production, it restores it as customers dash staging. And then optionally, an SSN parameter. So this is from the AWS console, if you haven't seen step functions. This is not how you create it. It's a visual representation of what you've written in JSON, or if you're using the serverless framework, you can also write it in there. What this allows you to do is take this to your analyst and say, is this the process that you think I should be performing? And you can iterate around that right there with the analyst until you get it right. And then once you have it right, you can take it out there and implement each of these states in the state machine so that you have it good. So here's the link to this service. Again, these slides will go around to you, but it's in the AWS Labs organization, just simply the AWS Backup DynamoDB locator. It uses AWS Backup, which is a managed service. If you have any sort of what I call legacy services in your account, you should be looking at this. That includes DynamoDB. It backs up EBS volumes, backs up EC2 instances, the EBS volumes of EC2 instances, backs up RDS, backs up DynamoDB. Simple notification service, if you're not familiar with it, is a massive fan-out messaging service for building distributed applications. Lambda is our serverless compute service, which is essentially functions that we'll get into. I promise there's Go code coming. Step functions we discussed, and then DynamoDB is where we do the backup service, or the database that we're actually restoring. So this is just a convention here. Some people would argue against this, some people would argue for it. I like this when I'm working with functions that I know are coming from step functions because it allows me to see at a glance as soon as I open the file. What type of data do I expect to get here? And what type of data do I expect to return here? And this becomes very useful when you get into the console and you're looking at errors and you expected a DynamoDB restore table from backup output object, but in actuality you built some sort of custom object and passed it in, right? So when you try to execute this function, it will fail and return. And again, I argue that's as it should be. You're not taking some random type here and trying to deserialize it yourself into a Go struct. The runtime handles this for you. So all you have to do is choose the bits of your state that you push in, the runtime deserializes it, and boom, you've got it ready to go. This is just some basic code for opening up the service. This is what I referred to as the wrong way earlier, right? So you see we're not using dependency injection here. We just have a handler function that takes its context and input and creates a new DynamoDB object, not the DynamoDB iFace that we would expect. So to make this better, we would have a receiver right here that's a pointer to DynamoDB that you can either pass in from your test or instantiate inside if it's new. And for almost everything that you will create as one of these ops workflows, it is this simple. You create the input object to your API call, you execute your API call, and you return whatever you got out of it. And then it's just a matter of manipulating that state as you move through. This is, remember at the beginning I talked about, I'm sure that all of you are better Go programmers than I am. This is why. I don't have to think in very complex concepts in Go. I write very small, very fast, very simple Lambda functions. And the benefit of that is I can be certain early that they're correct, despite being in a lower skill level, because there's so much less to think about and so much less to cover. A very, very powerful tool. This, I apologize for, but this is how you define step functions inside SAM, which is our serverless application model. This is a portion of that JSON that gets turned into the flowchart that we saw earlier. And the most important part of this is this input path. This is the restore table from backup output, and I'll show you an example of what this looks like in the console. That's what I'm passing in as this input object here. DynamoDB restore table from backup output. And for clarity, I just named them the same, but you can name them whatever you want. And then the same thing, take the result of that function, whatever that function returns in its return statement, and put it in my state at the top level in a describe table output object. And then move on to the next phase. So I'm going to switch to some code now. Super. Sorry, I need to mirror my screen so I can look at it at some point. Any questions about anything we've covered so far? Super. Okay, give me just a second to well, okay. So here's our state machine. I ran it earlier today. Can everybody see this in the back? Is that big enough for you to see what's happening here when we get into the execution? So again, this looks familiar because this is that Amazon states language that we did before. And this is that same, this is that same diagram that we had. So I want to look at the first step, which is this restore backup state. So to do that, we'll go into this execution. And you can start by looking at the input. And this is all that it starts with. Remember I showed you that example? It's just a simple JSON object. This is the SNS message that came in from an SNS table. This is the resource, the table itself that was backed up, and this is the recovery point that we'll parse later. And then as you look through here, you can check the state at each step. So we start with that same state, and what we do is we call the restore backup. So the next step in the state, we said we were going to return it to a root level restore backup object, and you can debug that by looking at the output. And you have this restore table from backup output object. And when you go into the code here, you can see that we've called, can everybody see this? Is this large enough? When you look at our handler here, you can see that we've called the restore table from backup API call, and we just returned the output with no error. So that output has gone right back into the state. And each step in the state machine flows through like this. Again, there are several places that you can go in and find these events. So in this case, we have this backup job completed. And you'll see that you get it in multiple locations. You also get it into your logs. You'll get it when this function executes. And it's just a simple start-stop that tells us that we've kicked off the state machine. So that's the basics of the orchestration. What I'm going to do now is go into a section of a workshop that I'm also going to provide to you that is very Golang specific. And so this is the part where we talk about SAM local, which is our tool for running your Lambda functions locally. And it will show you how to debug your Lambda functions locally, even though they are written for and compiled for a Linux environment. And then I'll show you SAM logs in the cloud so that we can see these as well. So this workshop I will give to you afterwards. It's always available for you to work through. You do have to have an AWS account, but you can just create the resources and tear them down on your own. In section 3, this is unit testing, which is everything that I spoke about earlier. And it gives you some more fleshed out examples of the dependency injection model. And again, we notice that our dependency is of the DynamoDB interface, not DDB, like we had written for the core generated one. And then again, we show you how to do the test here. Local debugging, I do want to spend more time on. This to me is the most interesting part of building with Lambdas. For a long time, what we heard was, yeah, but I have to deploy it to the cloud, and I have to run it, and I have to wait for the logs to sync, and I have to see what happened, and I don't understand how all that works. This gives you step-by-step instructions for building it. I'm not going to take you through those. I'm going to show you the debugging of the actual function call that we made earlier. To do it, you can follow these instructions yourself. It's the examples for VS Code. I've also done it for Golang. If you're like a Vengo user, it will work. I can't help you. Like I said, you're all better developers than me. But there are some steps. So SAM local runs a Docker container locally. And what it runs is a Docker container that's based on Amazon Linux, which is the same execution environment that you have when your Lambda function executes in the cloud. So the first thing you need to do is make a debug build for Amazon Linux. And then the next thing you need to do is you need to run that debug build inside that image with delve. And if you used delve before from the command line, it doesn't start executing your program. It runs and waits for a client to attach. And this client, in your case, in our example here, will be VS Code. Will attach, and then you can start walking through using the instructions from the client. There's also a delve CLI, and again, that's just beyond the scope of what I can do for you. And so I'm going to temp the demo guides again. And I'm going to make clean and make debug. So a couple things here. This Go OS Linux, Go Arch AMD64, these are to build it for the AWS Linux environment. I'm pretty sure everybody knows that you can make cross-platform builds with Go. It's a huge advantage of using it. And the first thing we do is we build delve from source. So now we have our binaries and we have the delve binary built. The next thing we do is this little magic incantation. Let me move this up and create something else to make this easier to see. This little magic incantation, which I give you in the workshop, just says, okay, pull the Docker container, run this function that's defined in my package, open the debugger on this port. The path to the debugger is here in this directory. Don't give it /delve, then it looks in a directory delve. Sorry, I didn't put that in there. And it looks in a directory delve for the executable, which it won't find. Some arguments and an event. This event is the same JSON that we saw in the console that we copied in, right? So this is the same execution that we ran earlier to restore a table. We're going to restore it again, but we're going to see what happens in the debugger. And so we see here, this is not an error. You will see this, and this is also mentioned in the workshop. Doesn't matter, ignore it. What we know is this is correct because it's launched the process with the arguments that we gave it. So again, it's loaded all the symbols, it's loaded your main function, and now it's sitting there ready to execute the first line, but you have to connect the client to tell it to do that. So in Visual Studio Code, this is the configuration for attaching to the debugger. This is also given to you in the workshop. Okay, you're not expected to magically know any of this. Name it whatever you want. And then this port just needs to match the port that you passed it on the command line. So if you don't like that port, that's fine. Use your own port, as long as you use the same one in both locations. So it's going to create a remote connection on that port, but the remote is localhost. And this is already configured. So when we go back to our code, remember the Lambda runtime will download everything, run main, get to the point where it's loaded the handler, and then it's going to sit here. So in this case, we get the input for the restore object, the output that we're going to return. We create the function, and then the heart of this, our business logic, is in this parse input function. So to see what that does, just like any other debugger, we set a breakpoint. And then you run this code, and now we can see that it's gotten to here, right? So just like any other debugger, we can set watch expressions, gives us access. So we haven't defined table name yet, so of course it's unable to evaluate it. It has step into and step over. I recommend step over. But just from doing this, we can look, and this is the same message that we got before. But now we've broken it out to the parts that we're concerned about. So we care about this sum table, and now we're going to compare that to our match expression. And so we have the input source pattern, this regular expression here, anything ending in table, so we expect to see a match, right? So we use a compiled regular expression, no error, and now we replace the string. So now we can look up at replacement. And we see that we replaced some table with some staging. So that's what we're going to restore this table as. This is a Linux executable. This is the exact same executable that we're going to push up to the cloud to run remotely, right? This is not a Mac build. But this is a big advantage because what's available to you in the cloud environment is available. It's using the IAM permissions that I have defined in my user here. So you want to be careful about the permissions you provide. But it's the exact same thing that we would normally do. And so in this case, I'll step through the rest of this function until we get to the restore point. We've got our target table defined here after this step. And what we've done is we've just taken the time from the message so that we don't have collisions if we were restoring tables. So what this specific example would do is take the timestamp, like a snapshot, and restore that every day, and then update your SSM parameter to point to it. And so now at this point, unless I did accidentally set another breakpoint. So now what this will do is return that output back to us on the command line. And so this is what went into that restore output object in the original JSON state, right? So we see this here with all of the specific fields that we care about. And now if we go back to the DynamoDB console somewhere, we see that we have this third table that's restoring just from the execution of the function. So we know that our function worked the way that we wanted it to. And now we can push it up and deploy it, execute it immediately. Okay, so I need to remember the name of the stack here. The last thing I want to show you is the SAM logs. SAM logs is a live tail of your function running in the cloud. So it connects to your CloudWatch log group and streams down logs that match. Even if you're using the serverless framework or plain CloudFormation, I recommend that you add SAM to your toolbox for the debugging and for the live tail, because it just needs a CloudFormation stack name and a function logical name. So in this case, we've called our app, our stack. I'm actually going to need to do so that is our stack name. And if we look at the resources from the stack, you see we have a restore backup function is the logical ID. And we get this tail here. And of course, it's not executing because we haven't given it any input, but it just sits there and waits. So we can go over to here and we can copy this input. And we can make another execution. And then we'll see this visual workflow updates as it executes through. So that's the same as the first event firing that kicks off our application. And we got a failure there, which we probably should have. And then we go back here and we see our logs give us the version of it. Table already exists exception, which is exactly what should have happened because we gave it the data from the last execution. So if we try to restore the exact same table name, we didn't account for that. And so we get the error. But this is the CloudWatch log that came down to our machine as it executed. So this is a way that you can debug all of your functions locally, step through and make sure that they're doing the transformations that you want. And then once you push them up, you can still stay from your terminal and see the changes that are being made in the cloud. So I'm going to stop that there. I will provide to you the repo. I'll provide you the workshop. I'll provide you the slides. If you work through the parts of the workshop that you're not already familiar with, it'll help you get up to speed and get your own machine configured to do this local debugging. Keep in mind that the local debugging is on a project basis, unless I just don't know how to use Visual Studio Code that way, which is always a possibility as well. But you'll need to configure that debugger for each one or copy the configuration across between projects. All right. Any questions? Do you want a microphone? Can I give you a microphone?
Do it for the live stream.
Just a quick question on SAM, first time I heard about it. What does the AWS SAM clause behind the same? Is that like what operating system? Is that the same as EC2 or AWS SAM?
So there's two parts to it.
Do it for the live stream.
There's the SAM CLI, which we use here, which you see. That's Python based, and it's executing on your local machine. The other parts of it, and even the live tail that you saw, is just a wrapper for the AWS SDK called to watch the live tail log view. The SAM itself, like as a model, not the CLI, is just a transformation or a transform for cloud formation. So all it does is it's a superset that then cloud formation processes down to vanilla cloud formation and then executes in the cloud. So the execution is happening in AWS. This is the same thing that the serverless framework does. If you're using it with AWS, it transforms their template into cloud formation and then executes it in the cloud. The benefits to that are that it's also serverless. You don't pay for the execution and generation of resources, but it's also native in the cloud. So retries and things like that are handled. Anybody else?
Is there with step functions an easy way of running that completely locally, or because I noticed you ran the first step locally, that it all do, and I assume it continue the rest of the operation in the cloud?
Yeah, so it does continue the rest of the operation in the cloud. That's correct. There is not an officially supported way of running the step function locally. The thinking on that is that the step function is the orchestration and coordination piece, and that's also where most of your IAM errors are likely to occur. So getting the logic right is something that we've done for the functions themselves, the Lambda functions. Grouping everything for the step function is kind of a philosophical debate. Like, should that even happen locally? Now, that said, this is a question that we get a lot. It's feedback that we get a lot. And I would say that we tend to take customer feedback very seriously. So, might be something that comes in the future.
I think it would probably reduce especially DynamoDB local.
Mm-hmm.
It's cheaper to run.
Yeah.
Just kind of lowers the barriers of entry with instrumentation.
Yeah, that's exactly right. There is a free tier for step functions. It's, I want to say, 4,000 state transitions per month forever. So like Lambda, it's not for the first year. It goes on forever. So you can test them out pretty well, but again, you want to make sure you have circuit breakers. If you're doing any sort of looping or dynamic parallelism, you want to make sure you put some guardrails around that so that you don't invoke 4,000 things in parallel every second for 2 days and then go home and leave it running. But you're right, that does help make for a more integrated local workflow. Anybody else? Any questions about the Go aspects of it, about the serialization? All of the SDK is open source. So you can go into GitHub and you can view how we load those functions and how we do the deserialization of the events and structure them into objects that we pass to. All of that is there as well. Again, because of my level, it's above me, but it's all out there for you to look at under that AWS SDK Go repository on GitHub. But I'm